Hello again, everybody, and welcome to another Geo-Institute live stream. If you consult your calendars, you will know that it is August and therefore still the summer of live, despite students all over this nation and all over the world having returned to class and doing their darndest to do their best in their chosen subjects. My name is Brad Keeler. I'm the director of the Geo-Institute. And yes, you have found Hour of Scour. We've decided before we went live today that it is probably the best show in the history of media devoted to scour and erosion. We do this once a quarter, and we're happy to bring you the world's leading experts on that topic. If you don't know anything about the Geo-Institute, after you watch this program today, head over to geo-institute.org, and there you will find out so many things about us, including that we're a technical society with about 12,000 members, most of whom are geotechnical engineers and or geologists, and that we are part of the American Society of Civil Engineers. And if you like what you see today, and we always guarantee that you will, dear viewer, you should click like, subscribe, and get notifications, and we'll let you know every time we post something to the YouTube channel. Since it is August 27th on this fair day, we're getting near the end of the fiscal year, and that may mean nothing to you, viewers, but that's how we measure our donations from you. If you have not yet made your contribution to ASCE or GI student programs yet this year, you want to do so. Just head over to geo-institute.org, click the button or the tab, I guess it is technically, that says student programs. You'll be directed to a donation page where you can choose how much you want to give and some great thank you items. And Stacy on cue will now hold up the Ralph Peck bobblehead, of which we have a limited number remaining. Look at that. He's holding the book, people. Peck Terzaghi and now Mesri book. You could have one of these on your shelf, a $96 contribution, and one will show up in your mail in a few days. With that out of the way, it is time for our feature programming today. Coming to us from San Marcos, Texas. She's a faculty member at Texas State University. It is our host of Hour of Scour, Stacy Kaleja. She's going to tell us about our guest today, and then we're going to get into it. Stacy, take it away.
Sweet. Thank you, Brad. You are right. I'm at Texas State. We've done enough of these. I will now correct you. It is San Marcos. We don't say San Marcos. I believe that's the California one. So next time we can say it properly. I'm an associate professor here. I do research in scour and erosion. I'm also the director of our University Transportation Center focused on coastal infrastructure durability. And so we also do a lot with scour and erosion, including a lot of offshore scour. So I am excited to have our guest today, Dr. Richard Whitehouse. He's the Chief Technical Director on Sediment Dynamics at HR Wallingford. His expertise in coastal and offshore sediment transport, morphology, scour, and scour protection. And he has over 35 years of international experience delivering practical solutions to engineering challenges, including the use of large-scale physical modeling. And he comes to us today from the south of England, right? South of England.
Yeah, the southwest in Devon.
In Devon, yes. So we are excited to have you here. If you want to, we can a few words of introduction, or we can hop right in. We have some opening. We, as a royal we, you have some opening slides to share that we can get the conversation going, and then Brad and I have been cooking up questions like all morning.
Good. I think you have. So yeah, thanks. It's great to be here. Thanks for inviting me. Thanks for teeing this up. I do have some slides, which I'd be pleased to share. So I thought about what I should try and show, and really I just wanted to get across some things I've been thinking about for the last few years. I'm going to be talking about the mudline. I know that's the place that geotechs and hydraulic engineers like to meet professionally. It doesn't necessarily contain mud. It might be sand, but it is the mudline. It's the expected design seabed installation level for your offshore structure. And it isn't static. It can change. It can go up and down. Terminology warning for you geotechs out there, I might use the word sediment and soil interchangeably. We can discuss that later if you like. Anyway, yeah, pleased to be here. So, yeah, I'm really going to be talking about some things that are related to putting offshore structures into the sediment transport environment. So my colleague and friend Richard Soulsby did a lot of great work on sediment transport and produced this really helpful diagram to show that the waves and currents are what stir up the sediment on the seabed. You get entrainment of sediment, transport of sediment, and then under certain conditions you get deposition. So this is going on most of the time. So above the seabed we have marine sediment transport processes. Below the seabed we have maybe geotechnical processes is an oversimplification, but basically that's, you know, that's where the geotech starts, I would say. If we put a foundation out there, such as a wind turbine foundation, and most of the work that I'm concentrating on nowadays with my great team are on offshore renewables, we can end up with, for a monopile, a scour hole around the foundation in the middle grey scale slide here. And then, of course, you have to get the electricity off to where you need it. So you have cables going in and out. They're buried in the seabed, they come out of the seabed, they go into the structure. So we have to take care of those as well, those high voltage cables. Now, some of these scour holes can be large. So this cross section on the right is through a tidal dominated shallow water site. And the scour depth at the monopile is around 6 meters deep. And the left to right along tidal axis extension is about 100 meters. So we're talking large features that we're engineering solutions for, or just learning how to manage the structure that has that kind of scour. So, yeah, large scale physical modelling. Our machine of choice is the Fast Flow facility, opened in 2014 in our Wallingford campus inside the Frood Modelling Hall. So it's a 75-metre long channel, has HR Wallingford design wave generator for regular and random sea state. Some nice big powerful axial flow reversible pumps. And importantly, we have a 1 metre deep sediment pit below the concrete slab. This is quite important because structures don't stop on concrete slabs, they go down into the soil. So for example, this nice picture showing one of our models in action with 3D printed and specially introduced 1:20 scale offshore workers there on the platform. That goes down into the basement below the concrete slab into the sand. So the other reason we need a basement is because we need to make very big models sometimes. So we had this interesting project where we were looking to be testing the performance of those orange frond mattresses that you can see in the top right hand corner there, at mitigating scour around offshore jacket pin piles. Now you need to do this at a large scale because you need to have those behaving mechanically correct. The fronds are going to be moving in the water. So to do that, we designed a half-scale, physical scale model. I justified to myself, and I think everyone involved, that we could actually use a half cylinder to represent this pin pile. And we drove scour processes up and down on this 100 tons of sand we introduced into the flume and created this very, very nice scour hole over a series of tidal cycles. We then did the mitigation testing. But that's why you need a basement, because you want to go big sometimes. If we go a bit smaller, but in the same facility, I got very interested in the whole tidal scour problem, and particularly thinking about it as a cyclic process. So again, sort of thinking about geotechnical problems where there may be cyclic loading. How could we characterize the tidal scour as a cyclic process? So we used a range of monopile structures with a mobile sandbed. fixed up the HR Wallingford scour probes on the front and rear of those. Those go down into the sand bed. We logged those at 1 hertz, so you could get a really high resolution, high precision time series of scour on the front and rear of the cylinder. We non-dimensionalized the scour depths with the pile diameter. We then work out the scour magnitude as the vector sum of those magnitudes. And then importantly, at the bottom of the scour hole, we can think about what the slope is between front and rear across the pile. And I call that the basal slope. And there's a special case of this, that at some point, if that's horizontal, the slope is 0. And that actually, I think, is an important point to bear in mind in tidal conditions. And I'll come back to that. So if we conduct the tests, we run a cyclic reversing tidal flow, which is shown by the orange lines in this diagram. We have a flow speed of about 38 centimeters per second going forward and then reverse over a trapezoidal signal. And we measure the scour going downwards from 0 as the scour depth increases, and then it fluctuates going back and forward as the flow goes forward and backwards past the pile. And this particular test was run for seven tidal cycles. So if we now think about having that pairwise data of 1 hertz, we can plot every pair of data as a pair of points on this nice diagram, which is a cyclic scour plot. So on the x-axis, we have the rear scour depth. On the y-axis, we have the front scour depth. Scour starts at 0 on a nice flat bed. It then heads off in a unidirectional flow. It heads off getting a bit deeper on the front. It then continues to get deeper on the front, following the line of these blue arrows. And on the rear, it is now getting deeper because the scour is connected, but it doesn't get as deep as the front does. So you get a slope across the base of the scour pit. If we then change to the cyclic flow, we get a different behavior. To start with, it starts like the unidirectional one, those yellow arrows going up. And then when you reverse that flow, you get this 90-degree turn in the scour plot. The scour heads down because it's now going to try and pick up scour at the rear probe. And at those red arrows, it's going through 0. So every time it switches, it goes through 0. That's quite awesome, I think. So you can then maybe try to distill this further into this 2-parameter plot type, which is the scour depth is this vector magnitude going up the y-axis. This x-axis is that basal slope between the front and rear. So for the unidirectional case, which is in this first graph, we end up with small scour at the beginning as it's just kicking off, but the slope is very steep across the pile. As the scour gets deeper, that slope relaxes and it follows a trend line that eventually heads off with a slope of about 6 or 7 degrees. And what we find with the cyclic cases, which are these other 3 plots on the right of the graphs, is that the same process happens, but you get this switching of slope. And the other thing is, as you go further and further up the plot in time, effectively, a number of cycles, you get this reduction in the amplitude of that switching of scour. And if you ran this for long enough, and I estimated maybe rather than 10 to 14 cycles, you might need 30 to 40 cycles. You might actually get down to the sorts of slopes that you would see offshore, which are maybe more like 3 degrees with a scour depth of 1.6 times pile diameter. So I think this provides some useful sort of basis for further analysis of cyclic scour processes. But what does it mean for foundations? So if we have a monopile foundation with a wind turbine, like I showed in the first picture or second picture, that's driven into the bed. Now, when we do our testing of the effect of seabed degradation with scour protection, as is shown on the left-hand plot with the bullseye colouring, everyone does it the same. You build a sandcastle of sand, you put rock on top, you run the test and you provide this falling apron of rock around the outside. That's great for proving your scour protection works as designed. If you want to get the dynamics of the structure as well, you can't do that. You've actually got to get rid of the sand by sediment transport processes. So we had a great project with University of Oxford and E.ON, RWE, where we used the fast flow, drove the pile into this deep sand bed in the basement, put scour protection around it, and then we had to work out how to get rid of that sand by sediment transport processes. So I thought back to my work on rivers back in my bachelor's degree and thought about base level control and thought, hey, we can recreate base level control in a flume. So on the left-hand side here, we've got the cross-section through the test section. We've got the sand. We've got either side of that pit, we've got some walls which are made up of bars going across the flume. So that keeps the sand in place. We can then put the flow, get the local scour. We then want to get the general seabed lowering or global scour. We can lift those bars up, which I had a willing team to help me. Here we are pulling bars up out the flume. And it actually worked. I was really quite pleased with it. Although it was about test number 6 where I got it absolutely perfect. And I got rid of the most sediment, because sediment wants to come back after you've driven it one way and you then turn the flow round. Lo and behold, it comes back again. Anyway, this all worked quite well, and I don't think anyone's done this elsewhere. So the important thing was it meant that the sand bed wasn't disturbed. And there was another side issue, which is we did some local scour. We then had to remediate with rock, but we weren't allowed to walk on the bed. So I devised an inclined full pipe system, and I was the conveyor belt putting rock down the full pipe. So that was pretty cool. Anyway, that all worked. The work's published, so there's papers available on that. So I just want to go horizontal now. We've done vertical, go horizontal. Think about pipelines, think about how you might protect valve stations in the middle of the sea. And subsea engineers will use things like this valve protection structure, which has a pair of skirted mud mats with perforations. The roof on top protects the valve from dropped objects. So a lot of geotechnical design work, structural design work done on this, but there wasn't much information on scour around these structures. So I put together a program. We had a paper out in OTC. So the nice thing about this, it actually allowed us to see some sediment transport processes in action. So I'm going to play this video. The flow's going from left to right. The thing to notice is this is for a flow case where the bed itself is not mobile. It's just scouring around the structure. And in the corner that's nearest us in front of the pipeline, you'll see a nice little spin up of an eddy. It'll pick sediment up and then it will be advected off down to the right-hand side. And the other thing to notice is that pipeline, which is partially embedded, this is heavily sped up, that now starts to have a free span formed under it. So this is one of these nice interface problems. You've got the protection structure there to physically protect the pipe, but actually there are some interesting boundary conditions for scour of the structure itself, but also of the pipeline. Periodically through the testing, we can take underwater laser scans, produce these great maps to quantify the scour and the bed forms. And then afterwards, of course, go in and inspect what's happened. So that's an interesting transition problem between the edge of the structure and the pipeline. If you want to protect your pipeline offshore, you may use an engineered rock dump placed over the pipe or cable. You may not be able to, or may not wish to put that very far along the pipe for various reasons, or you may be doing it in a series of campaigns. So the interesting thing there is that where you have an end, you again can produce underscour of the cable or pipe, and you can produce some very large lee wake features going down from the rock berm due to flow, vortex action, and turbulent energy. And we had an example of this in a project which worked on in the 90s. That was a while ago. So this was in a soft clay site. I think it was a 7 kPa, slightly plastic, silty clay, in about 10 meters of water, maybe 15 meters of water, with very fast currents. So the pipe was coming to landfall, which is shown on the top right-hand side of the diagram. The pipe was trenched. The trench backfilled, and the rock dump was actually placed on top of the trench rather than directly on the pipe. So in this bottom diagram here, you can see the blue line is the original seabed level. The berm is sitting above that level. In 18 days, we lost 6 meters of seabed. That's the pink line on the right-hand side, 8 meters on the left-hand side. And over the remainder of the survey campaign, the rock berm and the pipe were perfectly safe in that mound of sediment. This is a bit vertically exaggerated. I've cheated. If you make it 1-to-1, it's really quite a smooth profile, but to exaggerate the scour depth. So we ended up doubling the water depth either side of the rock berm profile to a distance of a couple of 100 meters. So scour can be quite an aggressive process. So finishing with a few points about maybe thinking about design and management. If you need to design a scour protection or a mitigation for scour, you need to think about two things. Firstly, you need to think about why it's required for structural integrity, but also you need to think about why it's required and maybe ask questions of other people within a project, because you may have a foundation discipline, you may have a cable or pipeline discipline. You need to make sure you get this interdisciplinarity between these packages to make sure that everything joins up and you get a good answer. So it may be, for example, in a wind turbine project that you have a foundation, you have a cable coming off to the right here, touching down on the seabed. We need to take care that the scour from the foundation and the cable are both working together. So say we need scour mitigation in that hole. Again, we need to think, what's the interaction with the cable? It may be doing a good job for the foundation, but we need to think about what it does for the cable. So we can manage this. You have to think about long time scales. We maybe have 10 years between the feasibility initial surveys and operational phase of a project when the structures are in the ground working. You're doing surveys, you're doing studies, you need to make a scour management plan, keep a track of data, decisions. And then when you go operational, maybe you've got another 30 years of design life and you might need to remediate at certain times. So with a managed plan, you can keep track of all of this and get a good, successful project. So finally, thinking about my own 30-year design life, I had a great opportunity in writing a book some years ago. Here is a copy. I had a scour burial model in there called Drambuie, as it turns out. And then with some excellent funding from CERDIP ESTCP and great collaboration with my friend Peter Menzel from Germany, we managed to do a really nice project on burial and migration of UXO for CERDIP ESTC program. And as part of that, with colleagues at Wallingford, was able to update the time evolution burial model. Got to test it against some data from the Delta flume here with Peter in the Delta flume, which was a pretty awesome experience as well. And we made an application, a modeling application of it to Fort Pierce in Florida for Hurricane Matthew. So that's all available. It's all good stuff. And I finish you with a question for you, Brad and Stacey. This picture on the left, field or lab? Thank you.
Going lab.
And I'm going to go to the opposite. I'm going to say field.
One of us is going to be right.
Well, you're right, Stacey. It's lab, but interesting that it kind of causes a bit of uncertainty in the mind because it's a pretty sort of natural looking field.
Yeah.
Yeah. I decided it was so awesome looking, it had to come from the awesome lab. Because if it's like a normal field photo, you're like, well, it's cool to capture, but this was in the lab, so we should highlight it.
That was one of those tests I showed where we were doing the global seabed lowering. So you've got the scour protection, the pile's been taken out, the image in the middle there where the black hole is, and then you've got these great features and falling apron, and yeah, all very interesting.
That's super cool.
Thanks for letting me run through that. Hope you found it interesting, and maybe you have a few questions, comments.
Well, we do, and we already have a question from the audience, so we'll get to that in just a few moments. And if anybody out there watching has questions, the right thing to do is exactly what our first questioner did. Put it in the chat box to the right of where you're watching this. I'm going to ask the first one today, and you'll see why in a moment. It's because the overwhelming majority of our audience is from North America and probably looked and said, H.R. Wallingford, that just looks like some company name, but it's a little bit different than that. Richard, can you give us a super high level view of how H.R. Wallingford came to be and the relationship with CEH and the research councils?
Yeah, okay, Brad, I'll try. So when I joined, which was 1988, we were called Hydraulics Research Limited. So HR is Hydraulics Research. And prior to that, we'd been Hydraulics Research Station, which was government research laboratory. We were privatised by Margaret Thatcher and her Department of Environment Minister, Michael Heseltine, in 1985 or thereabouts. Became a private, independent, non-profit distributing company. So we're kind of a hybrid. We're an independent research organisation, but we're also a consultancy and research organisation. So the HR in about the mid-90s, our marketing team decided we were known as Wallingford and we should be called HR Wallingford. They then invented the human resources industry, which meant when I rang up companies, you remember telephones, you had to ring through switchboards. You'd ring up, give your name, and they'd say, what's your company? You go, HR Wallingford, and they'd go, are you trying to steal our staff? Anyway, we know HR is hydraulics research, so we do like the HR part of it. We know what it is. CEH, you mentioned, well, the Institute of Hydrology was part of the HRS and was spun off and is now an independent agency and private company next door. So I think you've been there, Brad, yeah?
That's where I met you when I wore very inappropriate clothing for a 95-degree day with no air conditioning, and everyone else was in t-shirts and shorts.
Yeah, we don't have air conditioning in England, do we? No. In terms of UKRI, I mean, when we were first privatised, we did get some government science vote money, but and that was brilliant. But as the world moves on, you don't get that guarantee anymore. So we are able to bid for government research money. We are able to bid for UKRI money. We normally do that in collaboration with universities in the UK, with PIs from there, and we have some very good collaborations with our university friends here in the UK as well as overseas, actually.
So that's perfect. And now we're going to dive into the scour, and Stacey's going to take that first crack.
I have so many questions. I want to start with a softball question, but then I have the one that itches at my brain. But looking at your photos, I definitely saw a lot of local scour. We saw some general scour. don't know that we could say we saw a global scour, but what's the difference between the three scour mechanisms, since you went through kind of what's going on?
Okay, thank you for that. We have interchangeable terminology. I would say the only one that isn't interchangeable is local scour. So you put a structure, whether that's a monopile, a caisson, an embankment, a river training wall, you get local scour along it due to the flow turbulence and flow speed up around it. We then get some interesting divergences of terminology. So I think, but if there are any river engineers on the call, they can correct me. In the river situation, we would have general scour or contraction scour if you're going through a section and the bed's lowering in general. We like to use that in our own work to describe what happens offshore. So say you have a sandbank or you have a channel, subsea channel, and it's moving, you get general bed level change, general scour if it's lowering. We have a sort of interchangeable use of global scour and general scour depending on which part of the industry we're talking to. So global scour can mean general seabed changes that are not caused by the structure. If you're a local scour expert, then you would describe global scour as when you have a jacket structure, steel jacket structure, for example, you've got lots of cross members and bracing, and you get flow acceleration and turbulence generation from all of these. And that global scour is, as was coined for the Gulf of Mexico by Posey in the 1960s, dishpan scour. So you have dishpan scour around an offshore jacket in the Gulf of Mexico. That would also be termed global scour. It's due to this added turbulence effect. It may also be due to some kind of poor pressure effects in the seabed as a hurricane passes over, causing some soil loosening or liquefaction.
Now, this is the important part of this question, which I put a lot of thought into it. Which one of those is your favorite? It's like asking a geotech, what's your favorite failure mechanism, right? Like, but you got to have a favorite. What's your favorite dinosaur? What's your favorite scour mechanism?
I like local scour best because it happens fastest normally.
Okay. I do pay students to watch soil erode, and they do like it when it's a fast process. So I can understand that logic.
But I do like it when seabed features and coastal features start eroding and moving around, because it changes the boundary condition for your problem. And that really gets you thinking. So I've given you the answer, but I have to be a close second with general as well.
I mean, that's fair. The other question, and then I'll let you ask a question, Brad, because I have so many. When we were going through your slide deck, so our flume that I have commandeered here is very small. So sometimes we're very limited with what we could do. It's for teaching purposes. Most hydrologists don't like you to put sand in it. I was like, I'll put a sock filter over it. It'll be fine. My dean said that's fine. Okay. But very limited to what we can do. And you had the one where you had your like foundation, your monopile chopped in half. So I saw that, and the first thing I thought is, oh, he believes in symmetry, which I thought, in flume work, because water's flowing along the wall. So how do you justify it? Do you think scour holes are symmetric based on your experience? Do you do that all the time? Was it a special case?
No. So for monopile scour, I've only ever done it once, which was the case you saw. What I did, which seemed to work and make some argument of symmetry justifiable, is that I didn't put the half cylinder directly onto the concrete wall. I packed it out so that the wall boundary layer, maybe I didn't get rid of all the wall boundary layer effect, but I got rid of a good amount of it. I didn't measure it because I hadn't got an LDV in there. Sorry about that. But I packed it out so that the symmetry line was away from the wall. That meant that the flow could come along, the downflow could form, the horseshoe vortex had a chance of forming around the bottom of the cylinder as it went round it. And then there was some vortex action behind that could produce some counter-rotating vortices. I admit that therefore behind the cylinder you don't get that cross connection of the alternating vortices, but watching the way the sediment was eroded and picked up behind the cylinder, we had a stream of turbulent water coming off behind the cylinder. So the vortex action was happening. You saw eddy shedding coming off that one side. You saw upwelling as the sediment was eroded from the bottom. So I think you have to be careful with it to represent a monopile, but I think it can be done. In other experiments where we've looked at the effect of building cofferdams on river training walls or that kind of thing, of course you only have a half cylinder maybe, or a half abutment. We then did the other way around there, where we thought, well, could we predict the scour, assuming using a scour prediction method, assuming that we only had half the cylinder? It was effective, but I think it needed more work.
It can be done.
So if you're limited on space,
Why
you could try it, I think.
Hmm.
And by the way, small scale is good.
Small is beautiful.
If I had a small scale flume, I could be playing in there every day.
It is true. Yeah, I also run our large scale facility, and for us building something there takes 5 weeks versus in the flume it takes 4 hours. So yeah, there's definitely a helpful element of scale. Brad,
and before we talk about, yeah, I do, because I wanted to remember this, so I wrote it down, which I don't do very often. If someone is interested in partnering with you guys, I was going to say specifically for facilities access, but I think it's broader than that. What's the best thing for them to do, Richard? We've got a mix of viewers. I think we do have academics, we have consultants, we probably have people from much larger firms watching as well. What's the best way for them to start a conversation with you guys?
Send a mail or give us a call. We do have an office down in Houston.
Oh.
So we have an office in Houston, Italy. This is where I forget all of them. Kuala Lumpur. Those are the ones I'm remembering now, but there are more, I'm sure. But so yeah, you could reach out to my colleague Richard Lewis, who's down in Houston, and he'd be pleased to start a discussion with anyone who would like to do that. So we have been, in recent years, we've been doing work with Freeze and Nichols on the GLO Texas sediment transport study. So we've got that sort of collaboration that we've successfully delivered for your GLO. We're doing some consultancy work on projects already over in the US. A lot on ship passing studies, actually, in waterways for marine offloading facilities. And then the scour and sediment transport, again, partnering with researchers within the US. So the project I mentioned at the end there, that was part of CERDIP's munition response program. And in fact, a little earlier today, I was sitting on a call from a webinar from the MR program, where 3 of the key PIs were talking about a field experiment they've just been doing and modelling. So I think there are some good links. We'd love to foster those either through hiring out facilities or providing expertise, or maybe we have talked about, and one of my colleagues, Andy Manning, who works on fine sediment transport, he's been successful working with some of your academic colleagues on NSF UKRI co-funded programs. So there are opportunities there. I think you just have to get everything lining up. So there's a bit of luck there, but the first thing is to have the connections. That's the most important thing. That's what makes these things work.
Yeah.
So we're going to get to some viewer questions here in a minute. First, I'd like to get your thoughts on something and maybe some concrete changes that you guys have made to your research program because of this. We say this all the time in North America, extreme events have increased in number and gotten worse, et cetera, et cetera. I feel like you guys have probably had a more extreme case than us, where especially the remnants of hurricanes is one that I'm thinking of immediately. So when you accept aerial flooding, which has been a problem in the UK forever and ever, when you take that out, how have those increased events impacted your research program? I guess specifically in scour and erosion. What have you had to change because of it? And well, maybe that's the whole question.
Okay, I think in the fluvial side, because we also do fluvial engineering hydraulic studies as well as marine. I think clearly the magnitude and frequency of fluvial events has been something that has to be considered in terms of structural resilience. There's still a lot of work going on in the Thames estuary, the London River Thames estuary, to do with the flood defences there and the Thames barrier, which was tested in Wallingford back in the early days of the 80s, 70s and 80s, and is operating in the outer part of the Thames estuary to protect London from flooding. That has to be closed more frequently than was originally envisaged, and that's due to changes in the forcing from storm surges and from fluvial events as well. So that's a sort of example where you might see it. But I think offshore, so say we're designing an offshore wind foundation for a 1 in 50 year design event. Maybe now we have to think that you might get a couple of those. They might even occur in close sequence. So you maybe have to think about more frequent events of equal magnitude. I don't have the statistics on that. I have other colleagues who would be able to tell you more about it. But I think that's certainly the case for offshore structures. Maybe the design event doesn't need to change, but the duration of the design event or the number of times it occurs might need to be factored in. And I think that's happening more on the coast as well, where we're dealing with all the coastal protection structures, seawalls, breakwaters. There's a lot of added work going on to ensure that those are fit for purpose in this sort of increased stormy world we live in.
Fantastic. Okay, I think it's time for viewer questions. Stacy, do you want to hit him with the first one of these?
I will. So we got a great presentation from the viewer. What's a typical depth for offshore piles, and does the rock protection reduce the depth of embedment?
Okay. Yes, it can. This is a ongoing discussion with designers. So in the old days, Gulf of Mexico and any offshore pin pile type jacket, you might be driving those piles deep. They're of course they're large diameter, but they're, I don't know. I'm going to do it in. Should I do it in feet or meters? I don't know. They're a few feet in diameter maybe, and they go 40 feet into the ground or more. I don't know. I'm not doing this very well. But you might have an embedment to diameter ratio of order 10. For the modern large diameter offshore wind turbines, where maybe you have a 10-meter diameter pile at mudline, the new design methods, the PISA design method that's been developed recently with really good work by academics and industry in the UK. We're saving steel because you've got a lot more diameter, but you're only having to drive those maybe 6 pile diameters into the bed. So in terms of the thing happened that I warned might happen. My screen is locked up because of inactivity. Apology.
But we can still hear you, so that's the goodness.
Yeah,
And
carry
see
on.
you,
Anywhere.
so we're okay. We just keep it going, entertain the people during this time.
So the thing there is that your L over D for embedment is reduced in in relative terms.
Yeah.
But you still might need to put it quite a long way down. In terms of the point about scour protection, yeah, I won't talk while I'm doing this. Apologies.
I was trying to think of a good question for you, Brad, but then my face went blank. I was like, wait a minute.
Well, they are coming in. This is another good chance to remind people out there. If
Yeah.
you do have a question for Richard,
Apologies.
pop it in the chat box. We're going to do our best to get to everything today, but if you've got one, put it in there.
I'm really upset
And that
because I have 17 more questions, and now
Wow.
That's life. You can't get to everything. I have a bunch that don't have X's. That bought you enough time, Richard, I think.
Yeah.
Thank you. Yeah. I need to answer the scour protection question. Yeah, so like in that example I showed, if you pre-lay a scour protection and maybe you can drive the pile through it, or you pre-lay a filter layer of smaller diameter rock and then you drive the pile and then put armor rock on top. If you can hold that mud line at the installation mud line, you may well be able to save steel in terms of embedment length because you know that you're not going to have that bed lowering for scour.
That makes sense. So, different direction. Best question ever, not biased at all in my opinion, because it's not that I know this person who's an excellent engineer who did flume work with me. So I was so happy. Rudy Castillo says, have you evaluated the effects of shape on the monofile? Like, have you looked at like hexagonal shapes or different shapes instead of circular ones in the depth of scour, especially for offshore foundations?
Yes, so for things like gravity-based structures, we've looked at different shapes, hexagonal, square at different angles. And there was work done on slender piles by Mutlu Suma and colleagues in Denmark, where they looked at wave scour around different shaped structures. In the river environment, there's quite a lot of interest in streamlining foundations. And obviously, given the channel movement, the general scour of a channel, the meandering, you try to line up your bridge foundation to minimize that sort of angle of attack effect. But if the channel moves, you may not be able to keep it there. It might come at a different angle. When you're offshore, because we've got waves and currents in the North Sea coming, maybe the design currents and waves are coming from predominantly known directions, but they're probably not the same direction. And therefore, actually trying to put some streamlining or use different shapes is quite difficult to get an effect that you would reduce the scour. So, yeah, this sort of, effect of trying to reduce scour by using different shapes in the offshore environment hasn't necessarily yielded a good outcome yet. So if anyone's got some good ideas, like perforating, but of course, if you perforate, you reduce the strength of the foundation. So a lot of good flume experiments have shown advantages maybe of perforating or injecting air, sucking out air, putting water in, whatever. But yeah, at the moment, the circular pile is both from an installation point of view, maybe the amount of steel point of view, and the omnidirectional streamlining point of view, the preferred solution.
I will shamelessly point out that Rudy did perforate with such great success in the flume, but it was for riverine structures.
Has that been used in reality?
Actually, yes, they're about to install some in Miami as an abutment. So there's more work to come. So it is coming out.
I'm looking forward to following that. Thanks, Stacey. Yeah.
Yeah, our paper is in review. But I kind of along the same lines there. So, and then now I'm thinking about the opposite way based on what you just said, but that's okay. What's the most surprising thing an offshore scour has taught you that engineers, those inland engineers, might either underestimate or not consider? Because they are different, right?
Offshore scour. Well, I've done work on estuaries and rivers, and there are some surprises I've come across there as well. So I think all of us dealing with this problem have surprises from time to time. Also known as it keeps it interesting.
Huh?
And fun. I mean, if you're not having fun at work, then
what's the point?
What's the point? But yes, there are some serious things. So what offshore, I think what it's taught me is that in the days when we were working on primarily oil and gas projects, you were dealing with a smaller number of structures. They maybe were quite big. They had pipelines and risers and all these things going on, but you dealt with what was going on maybe in a more localized seabed area. And say in the North Sea, you put a steel jacket in seabed and you had 100 kPa clay, you might not get a lot of scour because that structure is quite static. If we now put one of these wind turbine foundations that's inherently flexible, and you produce cyclic amplitude oscillation at the mudline, the flow might not be strong enough to actually cause significant scouring, but because of this cyclic degradation or hardening, you actually get some change in the soil property there. And my colleague John Harris and I have shown from offshore field data, we put an empirical compendium of this data together, that even in 100 kPa clay for offshore wind foundations, monopile foundations, you can get significant scour depths of, say, half a pile diameter. So that was a really interesting thing that we perhaps hadn't thought about before we were doing work in the last 10 years.
It's good.
To build on that a little bit, we're going to use an ugly American stereotype here. We're a lot less aware of what the rest of the world is doing than you guys are of us. And I would bet there are a lot of people watching today who do not have a good feel for the difference in, we'll call it location, of offshore platforms and wind turbines than we have in the States. I mean, the first time I went to Scotland, I was shocked. I felt like I could reach out of the train and touch these rigs, and that's not an experience we have here. When you look specifically at scour, what impact does that have, rather than the deep water structures that we've got, like here in the Gulf?
Okay. Well, firstly, I mean, even though you could see those rigs, the majority of built structures, whether they're oil and gas or renewable energy, are some way offshore. There are some that are noticeably visible from the shoreline. And they're great because they're on a sandbank. Okay. Sandbank moves around and it keeps that really interesting as well. In fact, my general rule of thumb about my job, there are three things. There's not enough sediment, there's too much sediment, or it's the wrong type of sediment. So if you've got a sandbank, you might have to walk to your wind turbine. If you've got a big channel going by, you might have, your foundation too exposed, or you might find that you just don't have the right kind of sediment. Anyway, that's a bit flippant, but it is actually fairly true that most of these problems can be simplified into those three sort of categories. In the North Sea, are you thinking like the North Sea compared with Gulf of Mexico, maybe, or? Okay, exactly. So in the North Sea,
well, even the stuff that's going into the Atlantic, though, the turbines that have been put in the Atlantic coast of the U.S. are considerably farther offshore.
Yeah. Okay. So in the North Sea, we have strong tidal currents all the time. We then have storm surge currents coming around from the Atlantic. We have mobile sands and gravels. If we go to the Gulf of Mexico, we're predominantly perhaps looking at scour processes due to hurricane events. So they're episodic, but they're very significant. And maybe there's some other, like currents going on, oceanic currents. I think when you're on the eastern seaboard as well, in those sort of mid to deep water locations, again, I think, there are currents acting all the time. I think the episodic hurricane events or, nor'westers, whatever, are important. And actually, we see this in the Baltic Sea, say in the German and Polish sector. They don't have big tides, therefore the currents are not like the North Sea currents, and the Scour is dominated by episodic events. So I think when we get to hurricanes, and we've done work on some of your eastern seaboard wind farms, we've done testing of the seabed scouring and scour protection designs, and those hurricanes are quite noticeably different, particularly because of the long period of the wave as it goes past in very shallow water. So that's kind of maybe a bit of an answer.
I mean, I think your paper that you showed earlier on Hurricane Matthew must have supported that argument somewhat, because for people who do not remember, Hurricane Matthew hit an area of the U.S. East Coast. If you look at the map, it's that part of Georgia and North Florida that kind of is very concave, and it's extremely shallow water, way far out. I mean, can you give us a little snippet, a sneak preview of that paper for those who might want to go read this thing?
Okay, so that paper was...
My brain goes all over the place, Richard. I apologize, but...
So that paper was, as I say, it came out of our munitions response funded work from CERDIT. So the Fort Pierce site was a former US naval base from the Second World War, where they'd been doing exercises to plan for the invasion of Europe. So there was a lot of munitions left around. The majority has been cleared up. I mean, US Army Corps have dealt with all of that stuff. We were working with those folk, and we were interested in whether we could just put together a pilot modelling project to show that we could make some helpful predictions about, if you did have munitions in that kind of environment, what kind of scour burial you could get during a hurricane. So we ran the Hurricane Matthew event through our Telemap model, which is a ocean model. We got the waves coming to the shore. We generated longshore currents. We predicted the morphology change and the subtidal beach change. And in the model, we'd seeded some munitions, some surrogate munitions in our model. And using the Drambuie model I mentioned earlier, we were able to predict where you would see burial or exposure of those features. So it was really just a case of using that as an example to show the kind of behaviours you could expect to see if you still had a site like that you needed to clean up.
Yeah, that makes sense. So I have a very big picture question that I think as we approach the end of the hour of Scour. Looking ahead, thinking back on your career and looking ahead, do you think the biggest offshore challenges will come from deeper water, bigger turbines, novel floating structures, changing storms, or just the need to make more decisions faster with imperfect seabeds? I don't know. I feel like, what do you think? What's the big challenge that's ahead? Those are what I thought of.
Well, a big challenge is going into deeper water. of course, if you go into deeper water, the wave base is less bad, unless maybe you have hurricanes. We don't have hurricanes yet in the North Sea. So we may find that the scour in deeper water around a similar sort of monopile structure to that which I've been talking about is less severe, or it might just take a much longer time to form. So it may be that you do the modelling studies, using the metation hindcast, you can make predictions of how the scour will accumulate at the structure in deeper water. If it looked like you, in your steel design, you could allow for, say, 2 meters of scour in the design life, and you could cope with that in the length of your steel, maybe you just say, well, actually, given this environment, the mobility is not as severe as in shallow water. Therefore, I'm just going to monitor this. If it gets worse than that, I might need to intervene, but otherwise, I don't need to worry. So in that sense, it all becomes rather important about what the rate of scouring is. And to help with that, then you can take seabed cores, and you can do erosion testing, which we do in our lab as well, and then make predictions of the, if you like, the lifetime scour. I think the other thing is it's just the number of structures to deal with. So I know the pipeline engineers have all sorts of seabed they sample because they put this nice linear feature down, and they go, say, from a calcarenite through to a clay through to a sandy mobile seabed environment with bed forms. When you're building a smaller number of offshore structures, you can maybe site those quite carefully based on all the geophys, geotech you have. When you're building, say, 100 offshore wind turbine foundations, you have a lease area, you're going to be going across all sorts of seabed features. So I think it's the scale of it that's the challenge, and maybe moving into more areas that have other geohazards. So it's maybe you're not just dealing with tidal currents and so on. Maybe you're dealing with slope processes. But having said that, we've seen scour pits where we have survey data showing. So like that scour pit I showed at the beginning, that cross section, we were able to get survey data from one of our clients showing a scour collapse in one of those scour pits. And over a period of order 10 minutes, 450 cubic meters of soil collapsed from the side of the scour pit and went down into the bottom, and part filled it up. In active marine scour environments, where you get the spring neap cycle, you get that really big scouring effect in these tidal shelf seas, that's probably happening more than we think. So
yeah, that's crazy.
That's an interesting challenge.
That's cool.
I think we should wrap up with this. We did have this question in the chat to talk about any hot things that HR Wallingford or that you are working on right now in terms of scour. Is there any current project you want to pitch or something that's coming down the pipeline that you're excited about?
Well, we've had a lot of new projects coming along that I am excited about that I can't talk about.
I was kind of wondering that.
But they still involve a whole mix of foundation solutions. So monopiles are still extremely popular. Jacket foundations are very popular, particularly for offshore substation structures where you're gathering up all the electricity and then feeding it back to shore through an export cable. And they're getting bigger and bigger as the scale of the projects get bigger and bigger. I think the other topic of great interest is this whole interaction of the cyclic motion of the foundation for a monopile, for example. So we've tried to get some research together where we team up with academics on this, and we'd love to talk to anyone who's interested in that sort of work. We could have a really nice geotech hydraulics collaboration. We'd be excited to talk about that.
Love it.
It's fantastic. Well, we made it through another hour of Scour. I have to say a thank you to all the viewers, especially those who asked questions. That is what makes these so valuable. Thanks for putting those in the chat, and we appreciate everybody sticking around for those. If you liked what you saw today, and I always say you're here at the end, so you probably did, make sure you click like, subscribe, and get notifications, and we'll let you know every time we post something to the YouTube channel. Tell a friend to come watch this. It's going to be archived to the YouTube channel forever and ever, so you might as well. Or go back and check it out again and find Richard's email and reach out and collaborate and do stuff like that. Our next live stream, you've got a couple of weeks. Enjoy Labor Day weekend, and the summer of live will be winding down as we go through September. It'll be Carlos Santamarina's his third and final live streamed Cross USA lecture on geotechnics in the digital age. That'll be September 15th. You can, of course, register for free on our Eventbrite page. As always, they're all free. We'll have a lot more coming your way as we go through the fall and into the winter. Richard, thank you so much for joining us. I hope it was a good time. It was great having you here and hearing the depth of your expertise.
Yeah, I enjoyed it. Thanks, Brad. Thanks, Stacey. And thanks, Aurora, for setting this all up. I did enjoy it. And I hope there's some good things to take away and maybe have some follow-on discussions. And the great thing for me, having given the talk, it gets me thinking as well. So
perfect.
It's a good outcome. I'm very happy. So yeah, really enjoyed this. So thanks very much for hosting it and asking me to do this. It's been great.
We loved having you. Stacey, another great job as moderator. We appreciate that as well. Hosting, really, more than moderating. And our producer today was Aurora Flieger, and we will see everybody really soon with another Geo-Institute live stream.